We want here to construct and maintain the smallest sufficient set in near real time. So what is it about? It's about an online algorithm. So in the common setting, you usually think about offline algorithms where you first read the entire input and then you compute the solution. But often you want, while reading the input, to get an idea what the solution look like. So you want a solution for the part read so far. In the setting of strings, what you actually have here is a prefix. So you have read up to the ice length prefix, and you compute a solution for the current input. Then you update it by appending a new letter, and for this appended string, you update the solution. So you want to have a snapshot of the solution for each prefix, but of course this snapshot does not mean that you want an approximate solution, but a complete solution for the prefix read so far. And this is what online algorithm is all about, where we want to update incrementally the solution whenever a new letter arrives. Okay, there are some classes of online algorithms, and most of the online algorithms are analyzed just in the amortized case time. So basically you think about the entire time, how much it takes for the entire input. But often these amortized analysis neglect the worst case time per letter. And maybe you can have these high spikes and they can be arbitrarily high, but in overall, if you sum up everything, then it looks fine. But maybe you don't want to have these high spikes. And for that, there has been the term real-time algorithm introduced, which is very restrictive in the sense that here you're only allowed to have constant time per letter in the worst case. This is quite restrictive. In our case, we get a little bit weaker, which we call near real time, where the worst case constant, so the constant gets replaced by a logarithmic time bound. So what does it mean? You don't have this constant line in the plot, but gets a little bit weaker with respect to the index size. So the more letters you read, a little bit weaker it gets. Okay, what we want to do here is an online algorithm for sufficient sets, and we want to first introduce what sufficient sets are. And for that, we need two definitions. The first one is the right extension. So what is it? So first we fix a string of length n, t, of an alphabet sigma, and we use small sigma for its size, the size of the alphabet. And then we look at any substring of the text and call it s, and we take two letters which are distinct. And if it happens that sx and sy are substrings of the text, then we call sx and sy right extensions. So for instance, BA and BB are right extensions. So basically you have two different ending letters of S equals to B. Or for ABA and ABB, you can see there are again two different letters in the end, and the S is AB. So in both cases you have right extensions. They are not so interesting because there are so many. And what you want to do is you want to find a subset of these right extensions by using maximality. And then you get super maximal right extensions. So this maximality happens if you look at the property of being a suffix. So for instance, if you look at BA, but it's actually a suffix of a longer right extension, ABA. And if this is not the case anymore, that you cannot find any longer extension to the left, then you call it a super maximal right extension. So the RE, the right extension SX, is a SRE if there is no other RE such that SX is a suffix of it. Okay. So every RE is a suffix of some SRE. And we use this property for defining sufficient sets. So given a set of positions of your input text from 1 to n, a subset of it. Then this subset of positions is called a sufficient set if it contains the ending position of at least one occurrence of each SRE. So in this picture, for instance, you can see some SREs and some REs. You can just ignore here, for instance, the BA and the BB because they're just REs. Because by the property of an RE, you know that it is contained in one SRE, and you can extend it to the left, and you can see that actually the ending position are the same. So the original definition uses just REs, but you can just shrink it to SREs, which is nicer because we want to compute sufficient sets by SREs. Okay. Now we know what a sufficient set is, but why are they important? So in the initial paper, they have been introduced for compressed indexing. And recently, it has been shown that you can actually represent a text losslessly in order of the space of the number of SREs, words. And as a side note, the sufficient sets are string attractors, if you know what string attractors are. So sufficient sets is a nice SAM within indexing and compression. But here we look at not just an arbitrary sufficient set, but on the smallest one. So this has already been studied, the smallest one in its size, which is usually denoted by he. And it happens that he is equal to the number of SREs. So there is a one-to-one correspondence. And actually, what you can do is you can construct from the set of SREs one smaller sufficient set, one SSS, by just choosing for each SRE one occurrence, one ending position, and just mark this ending position. So these green marked ones constitute your smallest sufficient set, which we want to compute here online. Okay, this is the setting. Here in this talk, we make it a little bit easier in that we just change slightly the definition of online in that we do not append a letter, but prepend a letter in the online setting. So we scan the text from right to left instead from left to right. Okay. And for that, what we do is we maintain the suffix tree with Weiner's suffix tree construction algorithm, which works in this fashion. And during that, we maintain the set of SREs. And then we maintain from the SREs one particular SSS, which consists of the rightmost ending positions of the SREs. And the goal is to get everything in near real time is to use the suffix tree construction algorithm and maintain the SREs within the time of one suffix tree update. Okay, with that we need to define the suffix tree, which is a compact trie of all suffixes of our text. Here in this example, this is the suffix tree of this text here. So usually you define it with a terminal $sign, but we don't need it here in the talk, so it's omitted. Okay, now suppose we want to update the suffix tree. Now this is already constructed, but let's remove the last step. So we remove this leaf here, which corresponds to the first suffix, so the suffix starting at position 1. Because you can read from the root downwards to the number 1 the complete suffix AB and so on. So assume that we are at the final step in where we want to add the suffix. So you can see that all suffix numbers from 2 up to 9 are present, but not the 1, which we want to insert. And the idea is just to follow from the root downwards, reading the suffix. Basically the whole text. And you can see that we can read the AB, but then there is a B, but we want the A. So we have to branch off at the AB point. So this point is also called locus, and in this case the locus lies on an edge. What we do here is that we split this edge at the locus, the AB. Also the locus, so this AB, this is not just by coincidence, it's the longest common prefix of the suffix you want to insert with all already present suffixes. Okay, so we branch off here, we create a new node called gamma, and then we spell out the rest of the suffix and create a new leaf with the suffix number 1, because it's the first suffix here we want to insert. And we call always in this talk the new leaf lambda prime. And the rest is just to keep the same structure as before. Okay. This is what Weiner's algorithm does, and it also maintains some additional information stored in the nodes, which are called Weiner links, which we also need, and I just briefly introduce them. For that, so we have already defined what a locus is, and if it happens that the locus of a string is equal to some node, then we think about this node, let's call it alpha. And if it happens that the locus of some letter x prepended to the s, the string s, if it exists, then we create the called Weiner link, which we call x-link, because it takes the x and it points from alpha to this locus. And there are two conditions, so there are two possibilities. First, if it just points to a node nu, then we call this Weiner link hard, because it points to a node. And otherwise, it points inside an edge, and we call it soft. Okay, and this Weiner link maintenance and the suffix tree updates, they are not for free. And you can see from the history, so here it's we use time complexity TST for one suffix tree update, which creates a new leaf and maintains the suffix, the Weiner links, which, if you do it naively, takes a linear time just to traverse from the root to this insertion point. And you can see that you can do better. And there is a line of research going from log sigma amortized to some approaches which work in near real time. So any of these highlighted approaches would work in our setting. So what we want to do here is to take one of these time bounds, because they work in near real time, and our goal is to maintain the SREs within that time complexities to get order of TST time. Okay, so we need to figure out the connection between SREs and the suffix tree. So what is known in literature? It's a connection with REs, the right extensions, because if you look at the picture, the REs are exactly the set of path labels from the root to the first letter of each suffix tree edge. So basically here the A, the B, for instance. So this makes sense that we call an edge starting with a letter X an X edge. And there is a property, basically we sum up this property with a lemma, that if assume that there is a substring sy of the text, where s is a string and y is a letter, then this one is an re if and only if the locus of s is a node, and this node, let's call it alpha, has an y edge. And this is precisely what we describe here. You go down B, and then you read the first letter, which is an A in this case, and BBA is an RE. And that's all. So we have a condition for REs, a characterization for them. What happens for SREs? It's actually easy, because we can reuse this lemma. We only have to add a new condition down there, a third condition, and then it gets an SRE, if and only if for each hard link going from this node alpha let's say it goes to some node nu, we check that nu has no y edge. If it has a y edge, it means that we can extend to the left this RE, so it cannot be an SRE. So in this case, we just take all hard Wiener links and check whether there is no y edge going down there. And as a shortcut, instead of using notation, the string notation for SREs, we just use the node and the letter. And we use that in the following, by following the Wiener update, which we now explain briefly. So what does Wiener's algorithm do in one round? So one round, the idea is that you update the text to xt, so you prepend the letter, and you want to update the suffix tree. So what it does, it takes the last inserted leaf, call it lambda, of the old text. You walk up to find the lowest ancestor of lambda with an x-link, which we call alpha. Then we take the x-link, and let's say we go to a node gamma, and then we move down and insert here a new edge and a new leaf, lambda prime. So having that machinery, the Wiener's update already identifies the main nodes we need for the SRE maintenance, which we show later in the next slide. So in this case, we assume that the X-link leads to a node, so this X-link is hard. This is actually the first case we treat. In this case, we know that gamma and the new letter y, they constitute a new SRE because there is nothing going outwards. Otherwise, it would contradict the definition of alpha. So we already have here a new SRE found. And the question is now, if alpha y was already an SRE, then it no longer is. So we can delete it, because we can extend it now by prepending an X to get a longer SRE. Okay, this is the first case, a hard case. The soft case is quite similar. Now the X link goes inside an edge, so we have to split this edge here, create a new node gamma, and from gamma out we have the old edge continuing with the Z, and here we have the new leaf with the rest of the string. And okay, we have split it here, and what we can see, it's basically the old case, so the hard case, where we have already found a new SRE gamma y with the same idea, but actually we also have the yz now, which can be also a SRE. And similarly, like before, we have to delete alpha y, and or if it exists, the SRE y alpha z, because we have now can now prepend the X, and then we get a longer SRE. Okay, and that are all the cases we need for maintaining the SREs. So if we have the SREs maintained, basically we have to store somehow the information where the SREs are. And we do that by actually maintaining the rightmost positions of them. And this also constitutes the SSS we want to compute. So basically we use just one ending position of each SRE occurrence. And here we use the rightmost one. And we can just track that by using the suffix tree node, the gamma, because it already stores the leaves, and the leaves have the information of the starting positions of the suffixes. And what we do is we just use a bit vector where we flip the bit marking whether there is an SRE or not, because we also have to delete an SRE. But we use the rightmost position because we extend to the left. So on the left, things change, but on the right, there doesn't change anything if the SREs are unchanged. So this keeps the same, and that's why we use the rightmost occurrences. So the algorithmic summary is that we run the near real-time Wiener suffix tree update algorithm, where we receive the nodes which we need for maintaining the SREs. And the nice thing is that there are just constant many SREs that can change. So at most 2 insertions, at most 2 deletions per Wiener suffix tree update. And we use a bit vector that grows to the left. So the growing is also a constant time worst case, and marks the SSS positions, which constitute then the SREs. You can actually compute in the other way around, so the standard online way from left to right, by using the same complexities. So we get the same complexity bounds, but it's more technical, and that's why I didn't show it in on the slides, but just read the paper. So what are the complexity bounds? So we can maintain the SREs and our SSS set in order TST worst case time per letter, where again recall that TST is the time for a suffix tree update. And if we use one of the last 2 approaches in the table I've shown, you get this time, or you can get rid of the 2, so the squared exponent, if the alphabet size is small enough. So this is another solution. Okay, what we have seen, short recap, the small sufficient sets, they are a repetitiveness-based position set. So the repetition measure in the sense like string attractors, and the size of the SSS is the size of the number of SREs. There's a 1-to-1 correspondence. What we use is right to left input that matches Wiener's suffix tree construction algorithm, but again we can do it in the other way around from left to right, but it's a little bit more technical. We have seen that we only need to maintain or update a constant number of SRE changes. And so the takeaway is that the near real-time suffix tree maintenance yields near real-time SRE and SSS maintenance. So thanks for listening, and any questions are welcome.